Things are trying to figure themselves out. Well, let's try that again. It's always fun when technology doesn't work the way you want it to. All right, well, it's not working the way I wanted it to, so we're going to have to default to this. So I apologize for my handwriting, but I'm going to have to write with the mouse. Okay, so you were asking about number 8 on the study guide, right?
Yes.
That was the one? Okay. So when you want to convert it from polar to rectangular, you're wanting the any of those 3 equations to show up. So you're looking for like an r squared, you're looking for an r sine of theta, you're looking for an r cosine of theta, because then they're easy to switch out. So with this equation, you're close to having all 3 of them, but not exactly. Like it's just a little bit off. Like every single term in there is missing an r. So you just want to multiply the entire thing by an r. Oops. And with this one, it's not going to matter a whole lot because it's set equal to 0. But technically, you are multiplying that r to the right side as well. Sometimes it'll matter, just depends on what's over there. So now you have an r squared, a 4 r sine of theta, minus an 8 r cosine of theta. And now you can start switching things out. So your r squared is just x squared plus y squared. And what about the 4r sine of theta? Like the 4 is just 4, but the r sine of theta, that would turn into what?
A y.
A y. And the r cosine of theta
would be an x.
Mm-hmm. And then 0 is just 0. And you can totally leave it like this. It didn't tell you to put it in any type of format. So, but for practice, what equation or what would this actually draw? Like if you actually graph this out, what would it look like? Any ideas?
Circle.
Yep. You know, give you a circle. So it's right now it's not really in the best equation for a circle. Like you'd have to complete the square with the x's and then complete the square with the y's. You don't have to do that. You can totally just leave it like this. So Kiara, what were you wanting to do? Because you mentioned something about having a radical in there.
Oh yeah, I tried changing out the r for an x squared. Yeah, I did something weird.
Oh, okay, like changing out this r in the beginning.
Because at first I was like, isn't the 4 like an r? Yeah.
Oh, I get you. Yeah. Yeah, if it's not explicitly an R, then it's not an R.
Yeah. Got it now.
Yeah. Yay. Okay.
It seems like a very good writing. You don't need the technology. You can write with mouse. I mean, it's pretty clear.
Well, thank you. We'll see if your opinion changes as it goes on. Yeah, it's definitely not as fast, but it'll work.
Can you also show us how to solve 6C and 6D?
6C. Yes. Okay, so that was everybody that was wondering, that was number 8.
No, this
Okay.
is 6C, right?
C. Yeah.
C.
So the cosine of 2 theta, that one?
Yep.
Okay. So when you're solving a trig equation, one of the first things you want to make sure of is that the angle in every single function is the same. So like in 6a and 6b, that wasn't a problem because every angle was a theta. Well, in this one, now there's a problem because now you have a 2 theta and also a theta. So you've got to change them so that the angles match up. So you have a choice. You can either change the cosine of 2 theta or you can change the cosine of theta. And you typically want to change the one that's the easiest to do. So that is going to be the cosine of 2 theta, that first term. And we have 3 options for cosine of 2 theta. All 3 of them will eventually work, but one of them is going to be a lot faster than the others. So out of the 3 choices, which one was probably the best choice for this?
Number 2?
Which is?
2 cosine. I don't know how to say that little thing.
Squared?
Yeah, squared or theta squared minus 1.
Yeah, 2 cosine squared.
Yeah, cosine square minus sine square and convert sine square and cosine. So yeah.
Yeah. So this one's the best one to use because then everything's in terms of cosine. So you could use the other 2, but just like he just said, if you have a sine squared in there, like if that was one of the options you chose, you're going to have to switch a sine squared out with a cosine squared. So you might as well just go with the one that has all of the cosines in it anyway. Okay. This one's also nice to use because though the ones are going to cancel out. So 2 cosine squared, the ones are gone, and then you have the root 3 cosine of theta. And now we can solve because we can factor it. So how would you factor that?
We would take out a cosine theta.
Yes. Yeah, one of the first things for factoring is that you're trying to, always look for something you can factor out. Okay, and that's as far as you can factor it. So now just set each or solve each little factor for 0. So where cosine is equal to 0, and then where cosine is equal to negative root 3 all over 2. So where would cosine equal 0?
Pi 2 and 3 pi over 2. Or pi over 2.
Okay, I know. I was like, I think that's what you meant, but just in case. So yeah, pi over 2.
3 pi over 2.
3 pi over 2. And then for the cosine of theta is equal to negative root 3 over 2.
We have 5 pi over 6 and 7 pi over 6.
Yeah. And you can either go off of the unit circle, whoops, or you can do the triangles, or if you have another method you use, just keep using that. Because it's not going to tell you like how to solve it. You just have to solve it. So you can use whatever method you want, but if it's a free response, you got to show your work. You got to show at least this much. You don't have to list them out in numerical order either. You can if you want. But I usually just do this and call it a day. Okay, so how is that one? Do you have any questions on it?
No, this made sense. It was a lot easier than I was making it in my head.
Oh.
I got a little scared when I saw the 2.
The 2?
Like,
oh, in front of the cosine squared?
Yeah.
Okay. All right, how about for everybody else? Does it make sense? Any questions on where something came from?
I find sometimes the student, this is just observation from very far distance. Like the theta symbol is not in common language, frequent symbol, right?
Mm-hmm.
And if I write like a letters, I can probably write T faster because this looks like it's a plus, right?
Yeah.
As soon as I see the theta, I replace with the T and immediately replace cosine with some kind of maybe x and say 2x squared minus 1 plus. So simplify writing, but this is a perfect example, like a very clear. So
yeah, and you can totally do that. You can switch out something so it's a little bit nicer to see. So he's talking about like instead of like having the cosine squareds and stuff in there.
Yeah, substitute with some, let's say, x.
Yeah, just make it kind of visually nicer in a way.
It's difficult for grading later on. You need to know.
Yeah.
But
yeah, so you can switch it out and change it into something more like a polynomial.
that's right.
That's more standard. or not. It just depends on what you're comfortable with and what you like. Okay, so that was 6C. What was the other one? It was 6 what?
The next one after 6C.
Oh, D. Okay. Okay, so does everybody have this down? Can I erase it?
Sure. You
Everybody
can.
good? Okay. Okay, 6D. So sine of 2 theta minus cosine of theta minus 2 sine of theta plus 1. So we have the same problem as we did before, or sorry, the same issue. So the angles don't match. So we've got to get them to match. And usually you're changing the one that has like the coefficient in there, because that's the one that's going to have a formula that's kind of nice and where you can apply it, as opposed to just like a single theta or single x. So you're typically changing out the 2 thetas or the 2 x's or the 2 t's. So we're going to attack that sine of 2 theta, and what can we switch it out with?
Oh, 2 sine theta cosine theta.
Yes. Okay, and then every other term, we're going to just leave it alone. 2 sine theta, cosine theta minus 2 sine theta plus 1 is equal to 0. Okay, and with this, we have 4 terms in there. So when you're trying to solve an equation like this or a polynomial, if you have 4 terms, there was a real specific method that you had to use in order to factor it. And it starts with a G.
Grouping.
So we're going to group it. And with this one, we're going to group the first 2 terms together, and then we'll group the back 2 terms. So in the first 2 terms, we're going to pull out a cosine of theta. So 2 sine theta minus 1. And then the back 2 terms, all we're going to pull out is just a -1. Because when you factor by grouping, you're trying to get the terms to match inside of the parentheses. Because that'll allow you to proceed, and it'll tell you that you grouped it right. So our quantities in the parentheses match up. So that's what's common. So we're going to pull that common stuff out of there. And if we pull that out from both terms here, we're left with the cosine of theta. And also the -1. So now we can get the trig functions by themselves. So sine of theta is equal to 1/2. Cosine of theta is going to equal 1. So for the sine of theta equals 1/2, using the unit circle, triangles, or whatever, what would your 2 answers be? Like, where does sine equal 1/2?
5 or 6.
Mm-hmm.
Yep.
And the other one? Because sine is positive in 2 quadrants. It's positive in quadrant 1, and it's also positive in quadrant 2.
5, 5 or 6.
Yeah. Okay. And where does cosine equal 1? And keep in mind, we're solving on the interval from 0 up to, but not including 2 pi.
Just 0.
So just the 0. It does equal 1 at 2 pi, but that's not part of your interval, so you just leave it out. And there you go.
Very good. Yeah.
Okay, any questions on this one? Everybody's good? Okay. Yeah, that one was a little tricky because it pulled in a factoring method that you probably haven't used for a while. So there you go. Okay. Do you guys want to just keep going over the study guide, or what would you like to do?
There was like a rule for like when like you have like two like sine like 10 and then like sine 170 and then you add them together it equals 0 or something. Like 1 J, K, and L, there was like a rule of some sort.
Mm-hmm.
I don't remember the rules.
Oh. Do you have a preference for J, K, or L?
Probably K.
K. Cosines, okay. So cosine of 20 degrees and cosine of 160. Okay, so cosine of 20, like where would you actually put 20 degrees? Like which quadrant?
Quadrant 1.
Quadrant 1. And then you'd start to draw your little triangle, and you'd have an opposite side, and you'd have the adjacent side, and then you'd have the hypotenuse. And you'd have to, do adjacent over the hypotenuse, so on and so forth. And you could get an answer. If it was one of those special triangles, and this one's not. But that's okay, because for cosine of 160, where would you put that angle?
Quadrant 2.
Quadrant 2. So here's the 160. And when you have angles in quadrants 2, 3, and 4, you're supposed to use your reference angle. So if we draw the triangle, the angle inside the triangle is your reference angle. So what angle would this be? The green one. Yeah, it'd be 20 degrees. So then you would label your sides again, and you'd go, okay, so that's, whoops, not the letter I wanted. So you'd have your opposite side, you'd have your adjacent side, but since it's over here on the left, what type of a value is this going to be?
A negative.
It's a negative. So if you actually follow the formulas, like cosine's adjacent over hypotenuse, so that would just be x over h plus a negative x over h, right? Like they're going to be the same exact values because it's the same exact triangle, right? So what's that going to equal?
0.
0.
Yeah, this makes sense now.
Yeah, so you don't even care like what these, like the h, the y, and the x, they're going to be different numbers depending on what the angle is. But if your angles are the exact same thing, if you have the same triangle, one of your answers is positive and the other one's going to be negative, so they're going to cancel out no matter what.
Yeah, it's a very nice explanation. I will actually never use this in 100 years because I always converted this in the product between cosine, like a cosine A plus cosine B is 2 times sine, times cosine.
Okay.
That will give you 0, but this is a nice visual. It's a better for learning.
Thank you. So J and L are going to work well, J is going to work kind of the same way. L is a little bit different, partly because you can actually evaluate them if you wanted to.
Oh yeah, I actually did evaluate it.
You did? Which is totally fine. But like J, you can't really evaluate those without a calculator, but you're using the same process.
Yeah, because you would have like you would have 10 degrees in like the first quadrant and then 10 degrees in the third quadrant.
Yeah. So again, it's the same exact triangle, but one of them is going to give you a positive result and the other one's going to give you a negative. So they just cancel out. So for sine, they'll cancel out if one of them's if one triangle's on top, like above the x-axis, and then the other one is below. For cosine, they'll cancel if you have a triangle on the left side and another triangle on the right side. As long as the triangles are the same.
Very nice. Yeah.
Okay. Any questions on number or these two, K or J? Okay. Do you have anything else on the study guide that you want to hit for anybody? Like Kiara's been asking all the questions. Does anybody else have one?
I can ask one question, obviously. If graphing cosecant, that's actually 2c. What will be fastest way to graph that function? Cosecant of pi over 6 x plus pi over 2.
Okay. So for cosecant, I would just start with the period. And with cosecant, the period is going to be 2 pi over the absolute value of the b, or the absolute value of the number that sits in front of the x, or the coefficient of the x. Mm-hmm. So with this one, that's pi over 6. So when you divide by a fraction, it's the same thing as multiplying by the reciprocal.
So it's 12, right?
Yeah. Okay, so that's going to be your period. So with cosecant, that is the total distance from from start to finish. So with cosecant, it's the total distance from your first asymptote to the last one. Okay, there's no amplitude to worry about, so we can just go to the phase shift. So how do we figure out a phase?
The plus minus pi over 2, right?
Yeah, so just set your angle equal to 0. And then just solve for x, which a lot of times can just be done straight in your head. But if you can't solve it in your head, don't panic and go, well, don't know what to do. It's like, yes, you do. Just write it out and solve it. Because you've been solving these equations since pre-algebra. So move over the pi over 2, multiply by 6 over pi. And just reduce everything. So x is going to equal
minus 3, right?
Yeah. So if you, with this one, is the graph going to move to the left by 3 or to the right by 3?
I guess to the left, right?
Yeah. Okay, so with cosecant, that's a nice one because it's got an asymptote right on 0. So the periods doesn't affect 0, but the phase does. So you're going to shift that asymptote to the left by 3 spots. So it's just sitting over here. And then just take your period and add it to that asymptote value. So if you did -3 plus 12, that would give you a total of 9. So that would be the one that's way out on the far right. And then there's going to be one that's in the middle. So with anything, like how do you figure out what's in between or what's in the middle of two values?
Divide it up by 2.
Yeah, just add them and divide by 2. So -3 plus 9 is 6. Divide that by 2, and that gives you 3. And then for cosecant, it's normally the parabola shapes. Just the first one's up and then the second one is down. But with this one, you have to be careful because it's got that -17 in front of it. So that's going to flip it upside down and have it go like that.
Very cool. Yeah.
And then the 17, what it's doing, at least visually on your sketch, that's giving you the region where the graph doesn't go inside. So like the right side up parabola, the happy face, the smiley face, that one, the lowest it's going to go is that 17. And then the frowny face parabola, the highest it's going to go, it's going to come up and hit that -17 and then come back down. So no part of your graph should be between the 17 and -17. Now, what some people do, instead of just graphing cosecant as it is, what they like to do is they want to graph sine And so they'll put a sine curve in there, which is totally fine. And then they'll get cosecant based off of that one. And so if that's you, you can totally do it. So if you graphed a sine curve, it would go like that, more or less. So they would graph the green one first, and then they would get the parabolas and the asymptotes based off of that. And if you want to do it that way, that's totally fine too. You don't have to, but you can graph cosecant on its own, or you can graph the two functions together, whichever is the easiest for you. Just depends on how you.
Very good, yeah, very good.
Okay, so what do you guys think? Are you guys okay with this one? Any questions? All right. Let's see. How about the proofs? It's like number 5.
Yeah, that'd be a good one to go over.
Okay. Do you want dealer's choice, or do you want to pick one?
Let's see what you're dealing.
Your hardest proof.
I don't think you want that one. That one's not on here.
The hardest one.
The one that was on the quiz?
From last week.
Yeah.
There were 2 versions, and they were pretty much the same.
Yeah, there was the one on the quiz looked like it came from the homework problems. And I remember having trouble with it on the homework problems. So when it came to the quiz time, I still it's done.
That was one of those, you have to it's like you have like, it's like a polynomial again, but it's like identity.
Yeah, let me pull that up real quick just so I make sure I don't get something weird. It's like I remember the functions involved. I just don't remember which one had a minus. Okay, I'm glad I looked. I would have put the minus on the wrong spot. Okay, so one of them was secant to the 4th theta minus secant squared equals tangent to the 4th plus tangent squared. So either side is going to be totally workable because they're about the same difficulty. So one side is not really harder than the other one. And if you had the one that involves cosecant and cotangent, the steps are going to be pretty much the same with this one too. So you just got to pick a side. So which side do you want to go with?
I would go with the left side.
The left side? Okay. If you chose the right side, it's going to be really similar anyway. Okay, so what I would do with this is I would factor out what's common, because you have identities that deal with a secant squared, but you don't really have a good one for a secant to the 4th. So let's just pull out a secant squared. So secant squared, there's a Pythagorean identity that has a secant squared in it. So I'll just write it over here on the side, just so everybody can remember what it is. So like secant squared, that's awful too. According to the Pythagorean identity, what does that equal?
Tangent squared theta plus 1.
Yeah. So the secant squared that's over here on the outside, we're just going to directly substitute it with that tangent squared plus 1. But it's still being multiplied to that secant squared minus 1 quantity. Well, I'm going to do stuff with the secant squared minus 1 as well. And I have a couple of options with it. I can replace just the secant squared with tangent squared plus 1. Or if I just move the 1 over on that Pythagorean identity, I know that secant squared minus 1 is just tangent squared. So now I'm on a really good, I'm in a really good position because I now have all tangents, which is what I wanted. And then if I just distribute, everything pops out.
Perfect. Yeah.
So if you chose the right side, your steps would just pretty much go in reverse. Like you'd pull out the tangent and then use the same Pythagorean identity to switch out tangent squared plus 1 with secant squared, and then switch tangent squared with secant squared minus 1, and then distribute, and it gets you back to all the secants. So that's what I would do with it. It's not the only way. You could change everything into sines and cosines and work with those. That was quite lengthy. It was a much, might have been 3 times as many steps, because there's a lot of terms in there and there's just a lot of fractions, and it was lengthy. The other way you could do it, like instead of factoring out a secant squared, is just to use the Pythagorean identities right off the bat. So let me back up. Like secant to the 4th, a lot of people panicked. They're just like, oh my gosh, I don't know what to do with that. Well, if it's a 4th power, that's the same thing as saying, hey, that's like squaring a square, right?
That's right. Yeah.
So you could look at it that way. Like you didn't have to write it, but you could think it. And then you could switch out secant squared with tangent squared plus 1. Minus, and then switch out this secant squared with tangent squared plus 1. Oops. Forgot the square on that. And then it's just a matter of foiling and distributing the negative. So that'd be tangent to the 4th plus 2 tangents squared So that's the foiling part, and then the rest of it just distribute the negative into the second set of parentheses. And then just combine your like terms. So the ones are gone. Oh, I forgot the theta. You can combine the tangent squareds. And there you go. So if you chose the right side, it's pretty much the same thing. You're just changing tangent squared into secant squared minus 1 and dealing with that quantity. So most of the time the proofs have more than one way you can go. Some of them are a little bit more rigid, but most of them have an alternate way. It just depends on what you see. Okay, so that was the quiz question. Do you have any on the study guide that are just really tripping you up?
Why don't we do one on there? How about D?
D. Ooh, that's a good one. D. Okay, so I know which side I would choose, but what side would you guys want to start with?
Well, the right hand side seems the one that jumps out at me. I'm not sure if it's the right way to go.
Well, you can choose either side. That's kind of the nice thing about them, is that there isn't a wrong choice. It's just one of them is usually better. So we can totally go with the right side.
And is that the one you would choose?
It's like I would have chosen the left.
Left is a little.
Because it looks worse. But both sides are going to work.
If I can, I try to avoid the tangent side.
You avoid the tangents?
I don't like that side.
Oh. It is kind of funny. Like everybody has a preference in their trig functions. I don't know, like there's, oh, I love tangent, or I hate cosecant. Tangents to me are kind of nice because you can do some stuff with them, like tangent. Like, so with this right side, if we're going to go with it, what would you want to do with the tangents?
Probably sine over cosine.
Yeah.
Can I ask one question, gentleman with the bikes on the background?
Yes, sir.
What kind of bike you have? This is a two road bikes, right?
Yeah. One's a Cannondale and the other one's a Specialized.
Very nice.
Well, thank you. I enjoy a good ride.
So are you riding in Folsom or else?
I live down in Gold River, so I ride up through Folsom and on the back roads and down
Johnny Cash, the trail for.
I like Johnny Cash, sure. Yeah.
Okay. Thank you. Yeah.
I have a mountain bike up on the wall you can't see.
Nice. That is a fun area to be in. Okay, so yeah, I would change them to sines and cosines, mainly because you're trying to get to cosines anyway, so you might as well change them to get a cosine to come out of there. So sine A, sine B, all over cosine A, cosine B. And you even got a fraction to show up, and you want a fraction in the answer. All right, so what could you do now?
Action of the other one.
Say that again.
So you would put like cosine A over cosine B over cosine A, cosine B.
Yeah.
That's right.
Mhm. Yeah, just start combining the fractions together, so get that common denominator. So the 1 is nice. So I'll just change the cosine A, cosine B over cosine A, cosine B. And then you still have the other one. And you don't need to change it. Because it has this, it has a common denominator already. And now that they have the same common denominator, write everything into one big ol' giant fraction. So this is where it's kind of nice to keep in mind what you're trying to get to, like what you want this to come out as. So if you compare it to what the answer is supposed to be, you have the right denominator. So we're not going to do anything with it. So we're going to keep the cosine A, cosine B. It's the numerator that we need to take care of. So the numerator, you want to make it cosine of A minus B. Well, that has a formula, right? Like that's the difference one. What does cosine of A minus B actually equal?
Cosine A, cosine B plus sine A, sine B.
Mm-hmm. Right. And is that what you have?
Yeah.
Yep.
Yeah. So that becomes cosine A minus B.
And there you go.
Just like that.
So sometimes if you're stuck and you're like, how does that turn into that? Just look at it and go, is this actually an actual formula? Because sometimes it is. And it's like, bam, you're just sort of done. Oops. So if you chose the left side, your steps would pretty much just go right in reverse. So you could change the cosine of A minus B into cosine A, cosine B plus sine A plus, or sine A, sine B, and then split your fraction into the two. So you go from this big giant fraction to the step above, and then you would simplify them. So the first fraction would just be a 1, and then the second fraction would turn into the tangents. So if you just reverse your order, you'd have that proof for that side.
Cool. It always makes sense when I watch your videos and do them. Then I sit down and go, what was I supposed to do?
Yeah. What is this? The proofs are also kind of nice because at least you know what the answer is supposed to be.
Yeah, so you know what direction to go.
Mhm. And I'm not looking for, one specific answer. Like for the proofs where it has like multiple ways to get there, as long as your work is correct, whether you can do it in the most efficient way or if you choose one that goes in 20 steps, to me, it doesn't matter. As long as your steps are great and you get the answer and you didn't do any magical weird algebra, you're totally fine. A big thing with the proofs too is recognizing algebra to do. So factoring, adding fractions together, so getting a common denominator, splitting a fraction apart into smaller fractions, combining like terms. So just algebra that you already know how to do, you're just trying to apply it to this stuff. And then the second thing to look for is our trig identities, but that requires that you know what they are. Because if you don't know them, then you're not going to know what you can use. You're not going to know what sine of 2 theta is and when to use it if you don't know that identity, if you don't recognize it. And then the third one is to try something. Like you can't just sit there and stare at it. You got to try stuff and not be afraid to get it wrong, because you got to know what works as well as what doesn't. And if you're going, well, I don't know if I can do that, just try it and see if it works, because then you'll know. Okay, so I have a question for you guys. Let's do this. Let's take sine of 8 theta. What can you turn that into?
You can write a double of 4 theta or something.
Mm-hmm. Yeah. So as long as the number in front of theta, or the variable, is even, then you can use the double angle identity. So the double angle identity, we used it before.
To sine cosine, right?
Yeah. Oops. So that's the angle, or the double angle identity, and I'm going to apply it to this. And what a lot of people want to do is they want to change this number, this 2 that's sitting out in front. They want to change it to anything else. So they, a lot of times they'll go, hey, that's 4, or that's 8. It's like, no, that number doesn't change. So it's still going to be a 2 out of there. And it's still going to be a sine and a cosine, but what's the angle?
For 8 for 4 theta.
4 theta.
4 theta, yeah.
Because when you use that double angle identity, like the sine of 2 theta over to the 2 sine theta cosine theta, you're taking the angle and you're cutting it in half. So 2 theta goes to theta. And 8 theta, if you cut that in half, or divided by 2, That gives you 4 theta. So likewise, if you have sine of 12 theta, that would give you 2 sine of what?
6 theta, right?
6 theta. Okay, so as long as that number in front of theta is even, you can use a double angle identity on it. Okay, let's try this one. How about sine of 4 theta times cosine of theta plus sine of theta cosine of 4 theta. So we're going to take this entire quantity and we're going to rewrite it as something else. And we're not going to use a double angle identity on it. So we're not going to use what we just talked about because there's a different formula that is going to be a lot nicer to use.
It's one of the sum and differences formulas.
Mm-hmm.
Sum,
Yeah.
right?
Because the sum and difference formulas, they work in both directions. Oops. So you can go forwards and backwards with them. So is this going to be
5
the formula that goes with sine or the one that goes with cosine?
sine.
Sine. And is it going to be the sum formula or the difference?
Sum.
Mm-hmm. Yeah. So in general, if it's sine A cosine B, plus sine B cosine A, what does that equal? It's going to be sine of what?
A plus B, right?
Mm-hmm. Sine of A plus B. So you have this exact format right in front of you. So the 4 theta is like the A, and the theta is like the B. So you have that formula, so you can just go ahead and use it. So you're taking your two angles and adding them together. So sine of 4 theta plus theta. And then with this one, you can actually simplify it and just add the like terms. So that would be sine of 5 theta. So when you've got kind of like larger quantities involved with sines and cosines, you might see if, if the sum or difference identity could apply to that entire quantity, because then it would just collapse down into a single term. Because what a lot of people want to do is they want to take just sine of A plus B and they want to just expand it. And that's the only direction they ever look for. It's like, well, no, it can also collapse back down into just a single sign term.
Right. Yeah.
Okay, let's see, any questions on like this bottom half?
No?
Okay, so can I clear the screen?
Yeah.
Okay. Okay, let's let u equal 4i minus 3j. And we're going to calculate the magnitude of u. So is that going to equal 4i plus 3j? Like, is that what you get? Is it just for your absolute value every term? Or is it something different?
So need to draw the triangle and put I and J and take hypotenuses.
Yeah. This is not telling you to do the absolute value of both terms. So that is not what you do. So anytime it has like this double-sided absolute value, it is not saying, hey, just make everything positive. There's a formula for it. And it's equal to the square root of, you take the two terms, just the coefficients, and you square them. And if one of them is negative, then just stick parentheses around it. Because when you square any number, it's always a positive. So for a double-sided absolute value like this, it's asking for the length of your vector. So what you should get as an answer is a number and not a vector. So 5, 2 root 7, the radicals can still be in there. That's totally fine because it's still a number, but don't give me a vector because that's not what it's asking you to do.
Does the U have a line over it? Or like
It's not going to matter.
okay.
I stated it verbally. And I know you like formatting questions, so you just have to go with the instructions. Also, too, that practice quiz, that accounts for every single type of thing you will encounter on an exam or a quiz. So if you're like, well, it wasn't on there, it's like, well, it's probably because you need to worry about it. Because I wouldn't have asked you, yeah, a question that wasn't like that. Okay, so just keep that in mind about the double-sided absolute value. Because I can guarantee you that someone in the class is going to give me a vector if I ask for that. Because it happens on every single one. At least so far, at least in the 20 plus years I've been doing this.
I kind of debating once with somebody how to do good example of absolute value, which is not written in every math book. So I come up with the solution like when somebody is telling you, I have for you good news and bad news, right?
Mm-hmm.
And you say, give me bad news, give me good news only, right? So that's absolute value.
Yeah. That's funny.
Give me just good news.
Yeah, just the good news. I like that. Let's see. Do you guys want to do an example of like taking like an nth root of a complex number?
Sure.
That will be cool, yeah.
Okay, so let's do the cube. Get the cube roots of -4 plus 4i root 3, and we're going to leave it in polar form. So just really quick before we start to go through it, when it says to leave in polar form, what does that mean? Like, how should you write your answers? Or what format should your answers be in or look like? It's like, because if you don't know what polar form is, then you're not going to know how to write your answer.
So from x, y, we have to go to r and sine theta, or sine cosine theta, right?
Mm-hmm.
So that will be polar for
Yeah.
rectangular form. Yeah, okay.
So that would be, so he's right. It does involve the r and the theta. So this would be the r and then CIS
Of, yeah.
Of theta. So you're going to have a number here. It's like a 2 or 5 or 6 root 3 or something. And then you're going to have a number in for the theta. So something in degrees. And you don't have to use CIS. You can do cosine of theta plus I sine of theta if you wanted, or you can abbreviate it, whichever way. Unless it tells you to do it like this, then that's how you want to do it. Okay, so if you're looking for that polar form, the RCIS of theta, you now need two things. You need the R and you need the theta. So how do you get them?
Don't you third root -4?
No.
Can we take negative, or actually 4 outside and find the x and y and try to do tangent x and y and find the theta?
So like factor 4 out?
Yes.
Mm-hmm. Yeah, you can totally do that. No matter what you do to this, if you pull something out or leave it, you're going to want to probably graph it.
That's right.
So if you do pull something out, if you pull out the 4, oh, that looks weird. You can just, you don't have to, when you plot it or graph it, you can ignore the 4 if you want to. Just so you can kind of help, so you can recognize which special triangle you have.
Yeah.
So which special triangle is it? Is it the 45-45 or the 30-60? 30-60. And where's the 30? Is it up here on the top or at the origin?
It's at the origin.
It's
On
the
the
30 is actually up at the top.
Yeah.
Because the 30 is always across from the 1. And then the 60 is always right across from the root 3.
Okay.
So it's going to be your 60. So your hypotenuse is now
2.
2. So just don't forget that you pulled a 4 out of everything. So if you multiplied everything by 4, the R that you're really looking for is not 2, it's really going to be 8. And then the theta is not going to be the number or the angle inside the triangle because you're in quadrant 2. The theta is what rotates all the way over there. If it's in quadrant 1, then yeah, it's the angle inside the triangle. But if it's not, then you got to figure out what rotates over there. So the theta is actually 120. Okay, so now you can start to go into your formula. So now you can start to cube root stuff. So you're going to cube root the R, and then it's the CIS. You're going to take your theta. Oops, I guess I can actually take the number. So the 120. And you're going to divide it by something. So what would you divide it by? Well, I'll give you a hint. We're doing the cube root. So you're going to want to divide it by
3.
3. So if it was the 6th roots, you would divide by
6.
6. Okay, and then it's going to be plus, and then it's that 360K. And you're going to divide that by 3 as well. So you can simplify it down. So the cube root of 8 is just 2. And then CIS of 40 degrees. Plus 120K. So now you can start to get the roots. So if you're doing the cube roots, like how many answers should you have? So you only have 1 answer, 2, 7. How many answers are going to pop out of this? I'll give you a hint. What'd you divide by earlier? 3. So you should end up with 3. So if you're doing the cube roots, you get 3 answers. If you're doing the 4th roots, you get 4 answers. If it's the 5th roots, you get 5. So your first answer, that's why they call it like z sub 0, is because it's when k is equal to 0, you're plugging in 0 for k. So if k is 0, that's just going to be 2 CIS of what?
40.
40. And then for your next root, that's when k is 1. So you can plug in 1 for k. And then the second one, the next one after that, plug in 2 for k. And then if you wanted more, plug in 3 for k, 4 for k. It just depends on how many k's you have. The other way to think about it is whatever number's in front of the k, you're gonna add that every single time to give you a new answer. So 40 plus 120 would give you 160. And then if you added 120 again, 160 plus 120 would give you
280.
280. And there's your 3 roots. Now, just in case, like something you might forget, like, and just kind of get in this mode and just keep adding 120 over and over again. If you added 120, so you're like, okay, so Z3, you added 120 again, what's 280 plus 120?
100.
400. Do you see something weird about that?
Yeah.
What's weird?
That's
Another 40, right?
Yeah, it's over 360. So if you add it again, like if you add in that whatever number you're doing, if it comes out over 360, you've gone too far. So you just cross it out and ignore it. Because all of your angles should be 360 or less.
Oh, it just ends up repeating.
Yeah. Yeah, it just starts to go around the circle again and again and again and again. And there you go. All right, so I've got another question. What if I tell you that 2 vectors are orthogonal, what does that mean?
Dot product equals 0.
The 2 vectors, if you take the dot product, it's going to equal 0. What else?
Doesn't have something to do with 90 degrees.
But what about it?
Is that like it's like the angle between them or something?
Yeah. The angle between the 2 vectors is 90 degrees. So if you drew the 2 vectors out, so you got one vector going that way, you're going to have another one going like that, so that the angle between them is always 90. So the 2 angles, or the 2 vectors, are going to be perpendicular. Okay. Oh, see, can I clear this?
Yeah.
Yeah. All right. Just really quick. If you have sine of theta equal to 1/2, and you're supposed to solve that for theta from 0 to 2 pi. what would theta equal?
Pi over 6, right?
Mm-hmm. And
5 pi over 6.
yeah.
What was your limitation on that?
It is the same as all the other ones from 0 to 2 pi.
Oh, to 2 pi. Okay.
Uh, okay, so that was the problem. What if I said, okay, evaluate inverse sine of a half? What would that equal?
Just pi over 6?
Just pi over 6. And what a lot of people want to do is they want to say that's pi over 6. Oh, and 5 pi over 6. Because of what they just solved for up here. They know that sine of theta equals a half in 2 different spots. So they're like, okay, so I'm just going backwards. So inverse sine is going to be pi over 6 and 5 pi over 6, but it's not. Inverse trig functions only have a single answer. And why is that?
So the range?
Because of the range. So the range for inverse sine, do you remember what it is?
So pi
It's
over
negative.
And a quadrant 1 and quadrant 4.
It's in quadrant 1 and quadrant 4. So it's going from negative pi over 2 to pi over 2. So your answers have to fit in that range. So that is only going to be enough to give you the one result. Because if you could get more than one, then that violates the condition of an inverse. An inverse, in order for an inverse to exist, it has to be 1-to-1. So if you're getting multiple answers, that's no longer 1-to-1. So for an inverse trig function, you can only get the one answer. No matter how badly you might want to put a second one, don't do it. Because if you do, it's automatically wrong. If it's only worth 1 point, you just lost a point just because you wanted to put another answer down. So inverse trig functions just give you the single answer. Okay. How about inverse sine of negative 1/2? And I'll give you the answer that a lot of people put, and they'll go, okay, that's going to be 11 pi over 6.
Or negative pi over 6.
So if a student puts that down, I automatically know it's wrong. So why is it not?
Out of range.
It's out of the range. It's bigger than pi over 2. So you can't use it. So you have to give an equivalent angle that fits in there. So the 11 pi over 6, like it's kind of there. Like at least it's in the right quadrant. But it's bigger than the pi over 2. So to fix it, you just have to rotate in the opposite direction. So if you're in quadrant 4, just rotate down.
Negative pi over 6.
So negative pi over 6. So inverse sine and inverse tangent, if the number inside of there is negative, it's like this, a negative 1/2, your answer is going to be negative as well. Because you got to rotate in the negative direction to get to quadrant 4. Okay, I think that is going to be our time for today. So we covered quite a bit. A lot of trig.
Very nice, very nice. I especially like because you're using very wisely the paper. I mean, there is almost no wasting of ink. To say.
Yeah, didn't waste the ink.
Yeah, that's really straight to the point.
Good, thank you.
Thank you, Dennis.
Sure. So if you have any other questions, just shoot me an email. And then, yeah, don't forget, the exam opens 8 a.m. Thursday and closes by 11:59 Friday night. And then don't forget about quiz 8. So that's been available since yesterday. So if you can't take it before you take the exam, like hopefully like a day before, just so you can have stuff, like if you get stuff wrong on the quiz, you've got enough time to study, figure out why you got things wrong.
That sounds great.
All right. So yeah, if you have any questions, let me know. Otherwise, I'll just grade what you send.
Everybody have a great day.
Yeah, you too.
Very good. Yeah.
Thank you.
You're welcome. I'll talk to you guys later.
Thank you, Professor. Thank you. Bye-bye.
Bye.
Bye.
See ya.
Bye-bye.
Oh, I found out because I'm taking